Hello, this is Kevin, and you're watching Google Engineer Explains. Today we're going to be talking about LeetCode, problem number 11, container with most water, and this one's medium difficulty. Alright, so for this problem, basically the idea is you're given an array of positive integers, and you basically want to find the two integers where if you were to have them as the two heights of two walls of that height and pour water into it, find the one that can capture the most amount of water inside. So in this example, let's say we have this height and this height. So that's the 8 and the 7. The highest area would basically be 7 height times 1, 2, 3, 4, 5, 6, 7. 7 across, so that's 49. And that's, apparently that's the biggest one for this example case. But basically, the height is going to be the smaller of the two sides, right? Because if more water were to come in, it would flow out from the one that is lower on this side. So basically, it's the two. When you're checking any two numbers, it's going to be the lower number times how far apart they are. And you basically want to find the two that gives you the most amount of water. Cool. All right. So for this one, I'm going to go over two approaches. One, the brute force approach, and the second one is a more optimal approach, which is in linear time, big O of n time, which you probably, in a real interview, I think it would be best if you were able to get to that point, because the brute force one is pretty simple, and it's more straightforward. Cool. So, but just for completeness, let's go with the brute force one first, just to illustrate. So I think you probably already have an idea of what this one might be. The point is, every two numbers you can calculate the area, and you just take the best area out of the whole thing. So that one would basically just be check every set of 2 points, right? So if you are given the example array here, right, what that might look like would be check 1 and 8, check 1 and 6, check 1 and 2, etc. Check 8 and 6, check 8 and 2, check 8 and 5, etc. Right? So that'd be the brute force approach. So I'll just go ahead and implement that, just to go ahead and show. Oh, actually, let's just talk about it. So this one is basically going to be time n squared and space. Well, you'll see that is constant space, but initially you'll just talk about the time complexity. It's n squared because you have to check every 2 points. And okay, so let's just do the implementation for the brute force first, just to get this out of the way. All right, so basically you do something like this. So you'll have a best case, which you'll compare against. Let's make some space here. For L in X range height, len height. For R in X range L plus 1, len height. All right, so these are the two indices, left being the one on our left side, and then right would just start from that left index plus 1 and iterate to the end here. And so you would say area equals the minimum, right, of height left and height r. So that's basically saying give me the smaller of the two lines and multiply by the distance they are apart from each other. So this is r minus l, that's like the width, and then min height part is going to be the lower of the two lines. Multiply those together to get the area. Then you say your best area is going to be equal to max your current best versus the area, right? You can even simplify this further by taking this and just directly putting it in here. Okay? And then return best. So I'll just run this, make sure it works. Cool, and submit. And while we're waiting for that, this best here, it's since we have all positive numbers, we can say it's best 0 because the area will never be less than 0. But let's say we also had negative numbers or any sort of global thing you're trying to compare against. You could also do something like best equals float negative infinity, just so when you compare against negative infinity, the first one will always be greater than this, so it'll take it over. But in this case, we have all positive numbers, so comparing against best is 0 is fine. All right, cool. And then looks like we had a time limit exceeded. So what is the problem here? All right, so let's just take a look at this guy. Oh wow, they give us this really long array, right? This is like so long, and you have to compare every 2 of these guys, and so there's so many. So like this, you can see how this type of approach would get really big really fast, right? Let's say it's n squared. You have to compare every point against every other point. So let's say you had 10 long of an array coming in. Your total comparisons would be on the order of magnitude of 100, right? 10 times 10, because it's n squared. Let's say you had 100 points coming in. It would become 100 times 100, which would be 10,000. So 10 becomes 100. 100 becomes 10,000. 1,000 becomes 1,000,000, right? It just scales up really fast. So the reason this is failing is because they're basically just giving us a test to test time complexity, and they're just trying to say like, oh well, if it's n squared, it's too slow, which it's probably the case. All right, so if that's the case, then we basically need to go for a more optimal solution, right? So let's look into that. All right, so optimal solution. All right, and this one is actually pretty clever. I kind of like this one. So again, let's take this input array here. All right. So let's do this. Let's say we check 1 and 7, right? And the height and let's call it width, I guess. So height is going to be 1, the smaller of the 2, and then width is going to be how far they are apart, which is 1, 2, 3, 4, 5, 6, 7, 8. So they're 8 apart. And so the area is going to be 8. Let's say we were to check 1 and 3. The height is going to be 1 again, and the width now becomes 7, and that's 3. And 1 and 8. Height again is 1. Width is going to be 6. And so that gives us 6. Why did I say this was 3? All right. So if you take the 2 ends like this, and you take the smaller of the 2 ends, right? And you just keep on, if you check from the end and you just keep going inward, then you can actually see that your best width is going to be the first thing you check, and your best height is actually going to be this smaller one, right? Because between 1 and 7, the best case height is 1, and then if you keep on going in, if the number is smaller than 1, then the height is actually that number. But if the number is bigger than 1, the best case height is going to be 1. So the best that this height column could be is 1 as you go down. And the best that the width could be is that first one you check. It's the farthest away. So if that's the case, then you already know that this one is the best case if you check 1 against everything else. So that's pretty important. All right, let me just go over that again. As you go down, if you check once again everything else, the height can never exceed 1, right? If the number is higher than, can never exceed the this one. If the number is higher than this one, it's going to be this value. If the number is lower, then it's not exceeding it as well. So the best case for this one, this column, is going to be 1. And the best case for this column is going to be the first one you check, because that's the farthest away. So basically, this first one is going to be the highest possible area out of all the ones you check. And this is assuming you're checking the lower one versus everything else. All right, so if we already know when checking the ends, the best area for the lower side is that area. I don't know if, okay, right? So when you check the two sides, you take the lower one, and you already know that's the best case for the lower one. So you actually don't need to check 1 versus 3, 1 versus 8, 1 versus 4. It's just going in through that. You already know that that's the best case for the 1. So when that's the case, you can just move on and go to 8 next. 8 and 7, right? Because you've already checked 1 against everything else. Now we'll do the same thing, but now 7 is the smaller number. So if 7 is a smaller number, we know if we want to actually do it this way, like check 7 against 6, 7 against 2, right? And that's because that's the only way that this this holds true where the first one is the best case, because again, we know that the best case is going to be 7. It could actually be lower too. If it's lower, it's going to be 6, right? It's going to be 2. But if, let's say, the next one was like 10 or something, the height would be 7. So the best case is 7. So to make it so that the best case is always that number, you have to check the lower of the two. Because if it's the higher of the two, let's say we're checking 8 against everything, then let's say there was another 8 somewhere in here, the best case height would actually be 8. Whereas the first one you checked is 7, so your first one is not necessarily the best case anymore. So basically the rule is take the lower one and check it against everything else, but and then the best area will be the first one you check. So 7 and 8, the width is now 7, that's 49. You already know that 7 against anything else cannot be better than 49 because it cannot be wider than 7, and the height cannot be higher than 7. All right, so that's basically the rule, right? You just take the two sides. So the algorithm looks like this, basically. Algorithm. Check left and right most heights. And then take the, and then calculate local area. Move in from the lower height, basically. Cool. So I'll go ahead and just do that implementation now. All right, so again, best equals 0, left equals your left index, right equals len height. Was it height or height? Height. Height minus 1, right? While L is less than R. The indexes can't be the same. And let me just see if this works. If it's an empty array, it will not enter here. That's fine. If it's a 1 index array, it will also not enter. Okay, it's fine. If it's a 2 index array, it'll do it once. Okay, that's fine. Yeah. While L is less than R, we can probably just take the thing from earlier. Just take this guy right here. Right. Your best area is going to be the maximum of your current best and your new local area, which is min height L times the minimum of those two times the width they are apart. Then turn best. I think that should be it. So I'll go ahead and try. Oh, it's going to infinite flow. And then if height L is less than height R, then L plus equal 1, else R minus equal 1, right? That's just basically saying, like, all right, if the height of this side is smaller, then we go in, the L goes in by 1 and we check 8. Otherwise, if this side is smaller, the R goes in by 1. So whatever the smaller side is, we go in by that side. All right, so just make sure this works. Cool. Cool. So this one is working. Let's just talk about the time and space complexity. Time, space. All right, so it's big O of n. And that's because you go through this while loop. You do one calculation, and then your index goes in by 1, either whether it be on the left side or the right side. And you only do this one calculation for each element in the array. So where n is the length of your input array. And then space is going to be constant space because we're just using a few constants in here. We don't have any external data structures that scale with the size of your input. So it's constant space. Cool, so that's basically this solution. Yeah, it just basically hinges around the idea that when you have two sides, the smaller side, you don't need to check all the other ones. So we can basically take this n squared and bring it down to n. So that's how you do this one. Yeah, let me know if there's any questions or other stuff. Please leave them in the comments, and I can respond to them. Otherwise, yeah, let me know if there's any other questions on LeetCode you really want to see or any other topics. I'm happy to cover. And if not, hopefully you found this valuable, and best of luck with interviews. All right, thanks.